centigrams.
Oh, yeah.
Let me be specific.
Yeah, she can do it. Okay.
Oh.
So remember, you have a Frere model that is dedicated to figuring out if something is a function. You have another Frere model dedicated to linear and exponential functions in tables. Can I see this, Saj? This is what I'm referring to right here. Look, this. Literally, guys. Linear versus exponential functions tabularly. We're trying to break it down as easy as possible for you to study from. And no, Mason, this is not a hint. This is saying get it out. Take notes.
Which means like value has a difference, right? And then a function is every input maps to one and only one output. And I just but if you want to make a note of that, just so you know the difference.
You ready? Oh, you're ready.
So,
Okay.
it's like we're
Yeah.
about there.
Okay. Some people it's just not getting the sheet out.
Oh.
It's not from.
Good job.
No, yeah, it should go ahead, but.
Sorry, we're missing last time, guys.
Yeah.
Alright, today we're going to be doing that what comes next, what comes later thing that we worked on Tuesday and a little bit yesterday. We kind of got into it. And then practicing with all of our different representations we've talked about. What are those representations? What are our mathematical representations? Table, verbal, graph, picture, algebraic, boom, done. 5 of them. Linear versus exponential, what we've been talking about for the past, I'm going to say week now. What is a function? How do you define a function? Every input has one and only one output. Perfect. What about a relation? What's a relation? Mapping inputs to outputs, that's it.
Oh.
Yep,
Okay.
we're getting there, guys. It's a relation is a function. Wait. A function is a relation. It's a special kind of relation, right? What is equivalent? What does that mean?
Wait.
It may look the same. It may look different, but has the same meaning.
May look different, but has the same meaning. We don't want to say equal because when we think of equal, we think they look the exact same. Like 3x is equal to 3x. What's slope? Rise over run. What is y equals mx plus b? What's that whole equation? Y equals mx plus b. What?
M is the slope.
M is the slope. What does this represent?
Mason said it.
When we look at this function or this equation, what should we think of? Linear. Y equals mx plus b isn't slope. It's our slope-intercept formula, but the m specifically is our slope, our rise over run, like Deshaun said.
One thing I do want to point out is Mason said this. What did you say the B was, Mason? The y-intercept. Guys, why is it called slope-intercept form? Because you need the m, the slope, and you need the b, the y-intercept. Like, we're not trying to do a mystery here. We're telling you what it is. One thing I do want to caution you, and I need y'all to hear me on this, and I need you to write this down. rise divided by run, or change in y divided by change in x, that's how we calculate slope. That's not what slope is. So be careful on that, right?
The nines.
Rise divided by run, change in y divided by change in x, that's how we calculate slope. But what is slope? What's happening between the m and the x? They're being what? The m and x are being added? They're being multiplied, because Lane, what is multiplication?
Repeated addition.
Repeated addition, so what is slope? It's constant, repeated, constant repeated addition. Wait, oh, was it there? Yes. Yes, constant repeated addition. Remember, there's multiplication because there's repeated addition. So be careful. Change in y divided by change in x, that's how we calculate slope. But slope is a constant additive rate of change. That's the name for the constant additive rate of change. Okay?
Alright, relation, we did that the other day. Alright, did we all get through number 4 yesterday on this what comes next, what comes later? No? Alright, so, get with your groups. You're never guess where you're gonna go.
Home.
No.
Yeah, I get it.
Vertical surfaces, we're gonna work on these. Y'all work through 5 and 6. It shouldn't take too long. We'll see, probably about 30 minutes, we'll see. Just for 5 and 6. But y'all go ahead and get up and get with your groups.
For 10 to 15.
You don't have it?
10 to 15 minutes for 5 minutes.
Didn't I give you one yesterday?
I got the other ones, but that.
You said for a copy, right?
I may or may not have belonged to hospital. I wasn't here yet.
They were killing me. Why should we not have one either? Well, we did, yeah, we're in the library.
No, he stole it. He stole it.
Oh, thank you, Jerry. And I think we're gonna get into quadratics more next week. That's what we're gonna focus on. But Dr. Johnson talked about. Yeah, Dr. Johnson talked a little bit about it, right? Do you guys remember when he was talking about the rate of change of the rate of change?
Yeah.
Second rate of change? That matches with parabolas. Yeah. Anyway, it was good to recognize that were we adding the same thing each time? No. What was this, 5? And then was there a constant factor? No. So it can't be linear or exponential, it's gotta be something else. So we could not do anything else here. Perfect.
Yeah.
Frozen.
Hmm?
We're frozen.
Oh, yeah, I'll fix that in just a second. I do want to just point out this graph over here, guys, that I talked about in the table, that I talked about with this group. we're going to clarify some language on that rate of change to see that table a little bit more. But notice if you make that graph, and I did have to use some of my knowledge of parabolas and quadratics to get the left half, but literally what shape does that create? You're not wrong that it's a curve, but I do want to point out, this one right here is a curve too, isn't it? That circled in blue? Huh?
She already said it.
So what?
What the shape is.
What's the shape? Parabola, okay. I heard you say curve, my bad.
No, she said it earlier.
Oh, I got you. Yeah, make sure that we don't just call it a curve, because guys, I'll go ahead and tell you this. There's only one line out there, like a line is a line is a line, but there's infinitely many types of curves. So we can't just say curve, that is not gonna get the job done, huh?
It does look like you.
Do you know why we don't want to call it a U? Well,
Because it also like,
so one, it goes on forever, to a parabola is defined by this whole complicated thing called a directrix and a focus, and it's not terrible, it's not stuff we're gonna go into. Yeah.
Is that a U?
Dog. Okay, get in here.
Parabola. Let's call it a parabola. Alright, let's go on to 6.
If you want to pair in your mind U-shaped goes with parabola, go for it, but the mathematical term is say what, Jordan?
I don't even know how to say it.
No, don't you dare call it a line.
Bro, wait. What is this? What, we just said it. What is this?
parabola.
Parabola.
Guys, it's spelled right there if you need help. P-A-R-A-B-O-L-A. Parabola.
It's okay. It's okay. We'll get there. We're focusing on that all next week. That's all we're gonna look at next week. Is parabolas.
Go ahead, I'm just,
Okay.
writing it out nice and large.
So for this next one, thank you those of you who are up here with me,
Not stupid.
looking at our resources that we were talking about. So, what was the first step y'all did to figure out if it was linear, exponential, or neither? What was the first thing you did looking at this? Figure out the rate of change. All right. How do you get from 10 to 2? What's the difference between 10 and 2? 8. What's the difference between 2 and 2 fifths? What'd you say? 8 fifths, right? Is that constant?
No.
Absolutely not. So we gotta see if there's a what?
A factor.
A constant factor, right. So, how do I set up my equation to find my factor from 10 to 2?
10 multiplied by 3 times that equals 2.
Equals 2. How do I solve this?
Divide by the reciprocal. Times the reciprocal.
Multiply by the reciprocal, right? We multiply by 1/10 on both sides. And you will see in a second why we do that. So what's 1 times 10? 10. And then we have 10 over 10, which is 1, because this is that, right? So those go away. So we just have F equals, what's 2 times 1? What's 1 times 10? 10. That can simplify to 1/5. We would like to. All right, how do I get from 2 to 2 fifths?
2 times F.
How do I get rid of this 2?
Reciprocal.
These go away. We have F equals 2 times 1. 5 times 2. So, we recognize already we have a constant factor. I'm going to do one more just so you guys can see why we use the reciprocal, okay? So we have now 2 fifths times F, oh, I don't like that, times F equals 2 25ths, okay? When you first look at this, how do you want to get rid of 2 fifths?
5 over 2.
You want to multiply by 5 over 2 to both sides. That is your reciprocal, right? Because, what's 5 times 2? What's 2 times 5? That turns into 1, which is what we want here. We just want 1F. Just have F. 2 times 5? 25 times 2.
50.
We said 50, right? Yeah. So that simplifies again to 1/5. So we have a constant factor. But it would get really hard. Do you guys even, if we divided both sides by 2 fifths, instead of doing the reciprocal, this is what we would have to do. If we didn't have a calculator, would we know how to do that? Absolutely not. So we're going to use our reciprocal because it simplifies this to 1 over there, because it ends up being the same thing. That's what you do when you divide by a fraction. It's multiplying by the reciprocal. So just use your reciprocals. Yeah? Perfect!
So what?
Yeah, 1/5 is our constant factor, which makes it what? Exponential. Do we know how we would set up, or how did you guys set up that equation?
I said y
You said what?
Y is equal to x plus
10x plus 1/5? What did another group get for our equation? Same thing? Alright, what is our formula to make an exponential equation? So this would be a linear, So- a times b to the x. This is our exponential function. If we do not know this, we need to have this written down. We need to know what an exponential function looks like. So what is my a here? Why is my, what does a represent? Don't give me a number, what does it represent?
Y-intercept.
Your y-intercept. What does this b represent?
Slope.
Not that, are we?
Constant.
Yep, constant multiplicative or constant factor. Okay? We need to have that in our brains, we need that written down. Do we have our y-intercept based on this table?
No.
No, we don't. Because we start at 1. That would give us our first point at 110. Is that on the y-intercept? Or the y-axis? No. We need to figure out what, when x equals 0, what is y? How do we get that using our table? If our constant factor is 1/5. So from 10 to 2, we multiply. Yeah, you would use the inverse. Yeah, you would use the inverse, or we could do what? Instead of dividing, what have we been talking about this whole time? The reciprocal. So, if we multiply each by 1/5, now we have some number. Here's how we would set this up. Our factor is 1/5, correct? So, our y value times 1/5 equals what? 10. We're trying to find when x equals 0, what is y? And we start at x equals 1 and y is 10. So we need to go back 1. We need to figure out when x is 0. How do I solve this? Write it a little easier. Multiply by the reciprocal. 10 times 5? 1 times 1? 1 times 1? So this is our y-intercept. 50. So what is my equation going to look like?
Y equals 50 times 1/5 to the x.
To the x. Alright? I want us to have that down. And now you can see that how this is starting to look. Our y-intercept is 50. Way up here. 110. 2, 2. So probably going to look more like that. Yeah. So upside down. Alright. Perfect. Does that make sense? How are we going to set that equation? If I were you, I would write this on your prayer model. Because we don't know it. Now we know it. We didn't know it. And we need to make sure we know it in the future.
So it was not 10.
Our y-intercept was 50. Because our table starts at 1. Your y-intercept is when x is 0. Right? Yep. This is your y-axis, this is your x. What do you mean? this is our equation. Because we use our constant factor. And our y-intercept. We had to solve for our y-intercept. We did not have that, because our table starts at 1, right? So, solve for that, and we got 50. That's what all of this was solving for our y-intercept. Okay? And then we plug these values in to this equation we know to get this. One thing to remember, guys, if we have an exponential function, what do we need in our equation? An exponent, right? It's exponential exponent. Exponent is literally in the word, okay? So make sure, if we're writing it, which one is this? Linear. Is there an exponent in here? So we know this is not going to work for our exponential equation. Because what is multiplication? Repeated addition, so we're repeatedly adding. And then what is the exponent? Repeated multiplication. Which is what our constant factor is. It's repeatedly multiplying each time, right? I personally think I should see a lot more people writing this down because we didn't have our equation, but
No, we should see more people writing this down. This is not personal.
I really think we should be writing this down, guys. On your fair model? You don't have your fair models for this year?
No.
You definitely do. So just, some tables will start at 1, some tables will start at 0, some tables will start at -3. You just need to be aware of where your values are and see if there is an x is 0, what is y. If there isn't, you need to solve for it. Yeah, if our x is 0 and you have a y value, you have your y-intercept.
Can I show one thing? Okay,
Yeah.
look, so Mason, notes right here. This is the point 110 that we started with. Is that the y-intercept? 1,10? Is that on the y-axis? It's close, but is it on the y-axis? Like, that's what we mean by y-intercept. It's the point on the y-axis. So if it doesn't have that value of 0 that Kowalski keeps talking about, it's not on the y-axis. That's the whole idea. That is what x value, written there. But what x value is this right here? And what's over here on the left side of the y-axis? And what's in between -1 and 1? Gotta have that 0. So pair that table with this understanding of the graph. It'll help you. You gotta have the y-intercept. Let me clarify that, because y'all were running into that issue before. You can do it without the y-intercept, it's just more complicated.
Yeah.
Find your y-intercept. It's not that simple equation, it's a more complicated one if you don't have the y-intercept. So Lane, you're good to go, Kayla, Jaden, you got all this stuff written down you need to? Huh?
Your student.
Say it again.
I wrote down your student.
Okay.
So let's say,
Samaja,
I'm gonna use an easier table.
Jordan,
X, Y. Let's say it starts at -3,
Jack, you awake?
-2, -1,
you written this stuff down?
right? Let's say we're given that. I'm gonna say, and I need, in order to write my equation, I don't know if this is linear, I just wrote never done it work. I need to find when x is 0. But let's say I have a table, it's already given to me.
Let's look at some more practice ones with this.
Yeah, that might help. We're gonna do a little bit more.
Yeah, let's just get we might need to see some new ones. You may turn that off.
Alright,
If you want to, just move you. Yeah.
you, is this?
It's. I would spend at least half an hour on this. And then start Tuesday with that domain. That's what I'm.
Alright guys, real quick, we're gonna come together before the bell catches us. Did we all get through the first 3?
Yes.
Yeah? Okay, so I wanna real quick show you guys, we went through the first one a little bit. This last linear one seemed to trip us up, okay? Showing the graph. Where is my y-intercept on this graph? 0, 9, we can see it. So our y-intercept at 0, 9. Bam. That matches, we're good. Now we gotta figure out our slope. What is slope? How do we find slope?
Rise up and run.
Rise over run, change in y over change in x. So I'm gonna pick a point on my line. We're gonna go here, okay? This point is 1, 2, 3, 4, right? 1, 2, 3, 4. 4, 6. How many? And if I'm at 0, 9 right now, real quick, change in y is what? How do I find my change in y?
0, oh wait, put your
You go down, you go.
y2 minus y1 over x2 minus x1. y2, 6 minus 9.
Why? Okay. Just do right side of the run.
Yeah, okay. How many do I have to go down? 3. And we're going down, so is it positive or negative?
Negative.
And we're going right, how many?
4.
Positive or negative? Positive, because we're going right. We're going up the x-axis. So rise, over, run. Does that match this? Done. It's really easy when you have a
Hey,
linear
guys.
graph.
We're gonna sorry, the bell's about to catch us. We're gonna continue with this for maybe 30 to 45 minutes tomorrow, but we're doing a DYU and demonstrate understanding with linear, exponential, and the identifying the type of representation and if relations of function tomorrow at the end of class. If kids want to use the point form or the slope, first slope, but if they ask for it, just don't push it. It's unwieldy, so it's more complicated than necessary, so.
I didn't know if you like rise over run.
Oh, yeah.
Oh, you do?
Rise divided by run, change in y divided by change in x, perfect. y2 minus y1 divided by x2 minus x1.
That's a lot.
There's no added conceptual understanding and kids make mistakes with it.
Oh,
What's the